it's a specific kind of set now. It's the natural numbers, the counting numbers. 1, 2, 3, da da da. So, big N, right? So the counting numbers, that's the set. And the operation we're talking about is multiply. Okay, multiplication. That's the operator. Multiply. So that operator takes two elements of your set. Right? So x and y, they belong to the set of natural numbers. So x and y belong to n. Okay, and you multiply those two, and you'll get a result. And that result, x times y, will also be a natural number. In other words, the result, x times y, belongs to n, belongs to the set. Okay? But no matter what your x or y is, so long as they're both natural numbers, right? So in other words, the product of two natural numbers is itself a natural number. Right? So the result is also a member of your set, in this case natural number. Okay, so that's an example of the natural numbers are closed under multiplication. Now let's give a counterexample where you do not get closure. So again, let's use the set big N, natural numbers, and this time the operator is going to be division, not multiplication. Now, in this case, n, this set, is not closed under this operation. It's not closed under division. Why? Because the result does not belong to the set. The result, when you divide, it does not belong to n. Now you can see that. So why? Yeah, because well, let's take two integers, belong to n. Two natural numbers, positive integers, belonging to n. So 1 and 2, for example. And now let's apply the operation divide. Right? So you get 1 divided by 2. The division is your operator. But a half, that's not a natural number. It's not a whole number. It's a fraction. Right? So it does not belong to n. So the result, when you divide two members of your set, two members of n, 1 and 2, when you divide, you get a result that is not a whole number. It's not a natural number. Right? It does not belong to the set n. A half does not belong to n. Okay? So therefore, this set is not closed under division, under this operation. Okay? So it is closed under multiplication, and it's not closed under division. Right? So, and then go back to the general concept of closure. Okay? So we'll generalize. So in general, you have a set S. Okay, and it's said to be closed under some operation P. Now here P was the operation, here was multiply, and here it was divide. Okay, so in general, some operation P, whatever, if the result, after you apply your operation to members, one or more, of your set, if that result also, if the result belongs to the same set, then you say that that set is closed under that operation. Right? For example, n is closed under the operation multiply. N is not closed under the operation divide. Okay? Is that fairly clear? All right. All right. Now, in this chapter, now it's quite a long chapter, right? Let me just check. I think the page number of the last page of this chapter is page 98. So let's see, what page number does it start? So it starts on page 31, 100. So it's about 70 pages roughly. Right? It's quite a long chapter. So in this chapter, 70 pages of it, we will actually prove bit by bit, it'll take a while because it gets fairly heavy. That the regular languages, that set, if you like, or AKA, also known as, it's synonymous, collection. So the collection, you probably see, the collection of regular languages is closed under all three of the regular operations. So if you take two regular languages, then if you union them, so A union B, the result here is also a regular language. Okay? It's closed. So it's closed under the operation union. And it's also closed under concatenation. You can take two languages, regular languages, and you can concatenate them, and you get this, and the result, this thing, is also a member of, it's also a regular language. It belongs to that class or set of regular languages. So it's like a set of sets. But you have to be careful. I think that's probably why they're talking about collection. Why are they using this term rather than a set of sets? You have to be very careful with sets of sets because you can get into paradoxes. I talked a bit about the Barber paradox a bit earlier, and work of Bertrand Russell and others. There are lots of paradoxes in set theory and logic, and that was the whole century ago motivation for trying to find a firm foundation for mathematics. People thought set theory would provide the basis for justifying all the proofs and concepts of mathematics, the foundations of mathematics. But all these paradoxes kept popping up, and it got very embarrassing. So Hilbert thought he found a research direction, and then along comes Gödel and completely upsets the apple cart. I've talked about that before, and I'll give a mini course on this fascinating topic. All right, and similarly, the star operation. So it's a unary operator, right? So the language A star that you get by starring A, is all possible combinations of concatenations of any length, right? Your concatenated string can have any length, so long as k is not there's no limit on k. So this set here of all these terms, these elements, also regular. In other words, remember a regular language, what that means? It means there's some automaton that can recognize it. Okay? So there'll be, in all three cases, you can construct an automaton that recognizes these three languages, these bigger languages, like the union of A and B, the concatenation of A and B, and the star of A. In each of the three cases, you can find an automaton that will recognize these three bigger languages. Okay, that's the statement. Now proving it, that's where I say we're now definitely into senior level. It'll start getting harder, more abstract, and will require a higher level of intelligence to follow it and manipulate it and master it than before, than say junior level. All right. I'll stop there, and then in the next session we'll actually start on our first serious theorem and proof. Okay.